Welcome back to QHSE Talks, where we break down the science of safety, decode the concepts behind the CSP exam, and equip safety professionals with the knowledge needed to lead safer workplaces. If you are preparing for the CSP exam, you already know something important. This exam does not reward memorization alone. The BCSP exam is designed to test whether you truly understand how safety systems function in the real world, how organizations anticipate risk, control hazards, and prevent catastrophic failures before they occur. And that is exactly why today's topic is so important. Today, we are breaking down Chapter 38, Management of Change, or MoC, one of the most strategically important programmatic systems within modern safety management. Now, many candidates initially underestimate this topic. On the surface, management of change sounds administrative, almost procedural, something that belongs in policy manuals, documentation systems, or management paperwork. But experienced safety professionals know something very different. Management of change is not just a procedure. It is one of the most powerful risk control mechanisms an organization possesses. Because in safety management, the greatest threats rarely appear when systems remain stable. The greatest threats appear when systems change. Think about the environment safety professionals operate in today. Modern industrial operations involve complex production processes, interconnected equipment, automated control systems, chemical reactions, energy transfer, and human interaction with high-risk operations. Whether we're talking about manufacturing plants, chemical facilities, oil terminals, construction mega projects, or logistics operations, these systems operate continuously and often at extremely high levels of complexity. And yet within these systems, change happens constantly. New equipment is installed, processes are modified, production capacity increases, new chemicals or raw materials are introduced, maintenance procedures are altered, automation software receives updates, temporary bypasses are installed, contractors enter operations, organizational structures shift. Every one of these adjustments may appear minor in isolation, but within complex systems, even small operational changes can trigger cascading consequences. A pump with slightly different specifications, a change in material compatibility, a different pressure rating in a pipeline component, a modified maintenance procedure, a temporary bypass that remains active longer than expected. Each one of these changes has the potential to introduce new hazards that were never previously evaluated. That is exactly why management of change programs exist. Organizations that operate under structured management systems, such as ISO 45001, ISO 14001, and ISO 9001, developed by the International Organization for Standardization, require formal processes to identify, evaluate, approve, communicate, and monitor changes before they are implemented. In addition to international standards, regulatory frameworks also recognize the importance of controlling change. For example, under the OSHA Process Safety Management Standard 29 CFR 1910.119, organizations handling hazardous chemicals must implement written management of change procedures that evaluate technical basis, safety impacts, operating procedure modifications, training requirements, and authorization before changes are introduced. Why? Because history has repeatedly demonstrated a painful truth. Many major industrial accidents were triggered by poorly managed changes. Not necessarily because organizations ignored safety, but because they changed something in the system without fully understanding the new risk profile created by that change. And that reality is exactly why the BCSP-CSP exam blueprint places management of change across multiple domains. From an exam perspective, this topic does not live in just one section of the blueprint. It appears prominently in program management, where safety professionals must understand the organizational systems used to control operational changes. It also appears in process safety management, where MoC becomes a critical barrier against chemical process incidents, equipment failures, and uncontrolled hazard escalation. And it even connects to broader risk management principles, because the moment a system changes, the entire risk assessment of that system may need to be reevaluated. So when you see management of change appear in Chapter 38, it is not simply teaching a procedure. It is teaching a philosophy of proactive risk control, a philosophy that says, before you change a process, before you install new equipment, before you modify procedures, before you introduce a new material, you must systematically evaluate how that change will affect the entire system. You must ask, will this introduce new hazards? Will existing safeguards still function correctly? Will operating procedures need to change? Do workers require additional training? Could this modification affect environmental compliance? Could this interact with another system in an unexpected way? Because once a change is implemented without proper evaluation, the organization may unknowingly step into a completely new hazard landscape. And this is where CSP exam strategy becomes critical. Many candidates approach MoC questions thinking they will simply be asked to define the term, but the BCSP rarely tests knowledge that way. Instead, the exam uses scenario-based questions designed to evaluate whether you understand why management of change exists and when it must be applied. You might be presented with a situation involving a process modification, a material substitution, a software upgrade, or equipment replacement. The question will then test whether you recognize that a management of change process should have been initiated before the change occurred. Understanding that moment of vulnerability during operational change is the key to recognizing these exam questions, because ultimately, the BCSP wants to know whether you understand something fundamental about safety systems. Organizations are not most vulnerable when they are operating normally. They are most vulnerable during transition. And that realization leads directly to the critical insight that the exam expects you to understand.
So you really have to ask yourself why the BCSP places such a heavy, undeniable emphasis on this specific process. Why is it worth so much of your grade?
It's because any organization, regardless of the industry, is at its absolute most vulnerable state when it is in a transition.
Because when operations are static and routine, the hazards are generally known, right?
Exactly. They are known, documented, and controlled. But the moment you introduce a new variable, a new machine, a different raw material, a software update to an automated system, you introduce unknown, unquantified risks.
Think about it like this. Imagine you are tasked with building a commercial airplane, but you're trying to build it, or maybe upgrade its engines, while it's already in the air.
Flying at 30,000 feet.
Right, with passengers on board. That is exactly what a manufacturing facility, a refinery, or a construction site is doing when they operate without a strict management of change process.
They're swapping out parts of the engine while it's running, basically hoping nothing falls apart.
That analogy perfectly illustrates the stakes here, and this brings us to a crucial piece of exam strategy for you.
Yes. When you encounter MoC questions on the ASP or CSP exam, they will rarely ask you for a simple dictionary definition.
You're not going to see a question asking, what does MoC stand for?
No. Instead, the questions will be scenario-based. The exam will present you with a complex, multi-layered situation.
For example, a scenario might describe a plant manager who decides to bypass a failing pressure valve with a temporary straight pipe.
Right, just to maintain production quotas for the weekend. And then the question will ask, what is the first or most critical step the safety professional should take?
And I see candidates get tripped up by these scenario questions constantly. They see the bypassed valve and think the answer is conduct a lockout tagout.
Or they see a new chemical introduced and think the answer is update the safety data sheet.
That is the trap. The exam writers know you'll jump to the tactical response.
But if the scenario describes a proposed modification, a temporary bypass, or a new introduction to the facility, the right answer is to initiate the management of change process.
Because MoC is the overarching umbrella. It dictates when and how the SDS gets updated or how the lockout procedure is revised. It's the gatekeeper.
Exactly. Let's dive into the actual text of Chapter 38 from Yates. The text outlines the foundational pillars of a MoC program and ties them directly to major regulatory standards.
Yates mentions ISO 45001 right out of the gate.
Which makes sense. ISO 45001 is the international standard for occupational health and safety management systems.
And that is directly tested on your blueprint under Domain 2, Topic 8.
Under ISO 45001, MoC is not a suggestion. It is a hard, auditable requirement. If an organization wants to maintain that globally recognized certification, they must demonstrate a documented, rigorous framework.
A framework for identifying and managing changes to their processes, work conditions, and equipment.
And from a strictly legal compliance standpoint in the United States, we have to look at OSHA.
The Occupational Safety and Health Administration mandates MoC primarily through its Process Safety Management Standard, PSM.
That's 29 CFR 1910.119. And OSHA didn't create the PSM standard in a vacuum. It was forged in the aftermath of catastrophic industrial incidents.
Primarily in the chemical and petrochemical industries, right?
Yes. Time and time again, investigators were finding that massive explosions, toxic releases, and fires were occurring not during normal operations, but because a facility made an unmanaged, poorly analyzed change to a highly hazardous process.
The Yates text also brings in the Environmental Protection Agency, the EPA, and their Risk Management Program, or RMP.
Which is interesting because it links directly to Domain 5 of the CSP blueprint, environmental management.
So why do both OSHA and the EPA require MoC with such strict alignment? How do they overlap?
The overlap is the physical boundary of the facility, what we often refer to as the fence line.
Okay, walk us through that.
Imagine a single unmanaged change in a chemical process. For example, substituting a specific grade of stainless steel piping with carbon steel.
Carbon steel that isn't chemically compatible with a new, highly corrosive catalyst they just started using.
Exactly. That incompatibility can result in a pipe rupture. That rupture exposes the workers inside the plant to a deadly vapor cloud.
And that is the occupational disaster, which falls squarely under OSHA's jurisdiction.
But that same toxic cloud doesn't stop at the property line. It drifts off-site into the surrounding community, potentially exposing schools, neighborhoods, and local waterways.
Which is the environmental catastrophe, falling under the EPA's jurisdiction.
The MoC process is the singular, unified shield designed to prevent both of those outcomes simultaneously.
Let me play devil's advocate for a moment here.
Yeah.
Because this is real life. If I'm an operations manager and I have production quotas to hit, I am losing thousands of dollars an hour when a line is down.
Right. Production is king in a lot of places.
So if a pump breaks, and I have a slightly different pump in the maintenance shed that can get us back online right now, I'm going to use it. When safety comes in demanding a full no-side review, I'm going to say it's just red tape slowing down the business.
It is the most common friction point you will face in the field as a safety professional.
So how do you defend MoC in that environment?
You defend it by explaining the financial and operational realities of unmanaged risk. On page 861 of the text, Yates points out the benefits of management of change.
You have to speak the language of the operations manager.
You do. You explain that MoC prevents catastrophic, uninsurable losses. It prevents prolonged, multi-month regulatory shutdowns that would cost 10 times more than the hour it takes to do the MoC.
There's also a psychological and cultural aspect to this that I think is critical.
Yeah.
If we allow that operations manager to just swap the pump without an OSCE, and nothing bad happens that day, we've just reinforced a dangerous behavior.
You are referring to the normalization of deviance. It is a concept heavily studied in system safety.
Can you break that down for the listener?
Sure. If a worker or a manager makes a small, unauthorized change to a process, maybe bypassing a safety interlock on a machine door to clear jams faster, and they do it without any immediate negative consequence, that shortcut becomes the new normal.
The deviance is normalized.
Exactly. Over time, these unmanaged, undocumented changes accumulate within the system. The safety margins are silently eroded until a catastrophic failure inevitably occurs.
Think of major historical disasters like the Challenger space shuttle or the BP Texas City refinery explosion.
Post-incident investigations almost always reveal a long history of normalized deviance and bypass change management protocols. MoC is the mechanism that forces a hard stop to that erosion.
Let's get into the actual mechanics.
Yeah.
The exam blueprint explicitly requires you to understand the MoC process prior, during, and after.
And Yates provides a definitive 5-step MoC process to help organize that.
Let's walk through this sequential framework so you, the listener, have it locked in for the test. What are the 5 steps?
They're logically divided across the timeline of a change. Step 1 is identify proposed changes. This is part of the prior phase.
Okay, step 1, identify. What's step 2?
Step 2 is prepare the organization for change, also part of the prior phase.
Then step 3.
Implement the change, if safe. This is the during phase.
If safe. I like that caveat. Step 4.
Embed the changes within company culture and practices. This is the after phase.
And finally, step 5.
Execute and monitor the changes. This is the ongoing after phase.
Let's really break these down, starting with step 1. Identify proposed changes. On the surface, identifying a change sounds incredibly simple. If management orders a new piece of machinery, they've identified a change.
But based on the text, this is actually the most common point of failure in the entire system.
Why is that? What are candidates missing here?
They are missing the critical distinction between a true change and a replacement in kind, or an RIK. This is a concept you must understand deeply for the exam.
A replacement in kind.
Yes. A replacement in kind means you are swapping a component with an identical component that meets the exact same original design specifications.
So if a 50 horsepower motor on a conveyor belt burns out, and I replace it with the exact same make, model, and horsepower motor from the exact same manufacturer, that is a replacement in kind.
Yes. In that specific scenario, no MoC is required because the risk profile of the system has not changed.
But I imagine it's rarely that simple in the real world.
Let me give you a scenario based on something I dealt with early in my career. We had a centrifugal pump transferring a mildly corrosive liquid. The impeller inside the pump degraded and needed to be replaced.
Okay, pretty standard maintenance.
Right. But maintenance couldn't source the exact OEM impeller. They did find one from a different vendor that fit the shaft perfectly, though. It looked identical. So they called it a replacement in kind and installed it without an emergence.
Let me guess. It wasn't actually identical.
Far from it. The metallurgical composition of the new impeller was slightly different. It had a lower tolerance for the specific corrosive liquid we were pumping.
Oh, wow.
Furthermore, the pitch of the blades was off by a fraction of a degree, which subtly changed the flow rate and the discharge pressure.
So what happened?
Within 3 weeks, the new impeller cavitated, shattered inside the housing, and blew out the mechanical seal, causing a hazardous material spill.
Just because of a fraction of a degree and a slight metal difference?
Because we failed step 1. We failed to identify that it was not a replacement in kind. And because of that, we bypassed the entire safety analysis.
That is a phenomenal example for the listener to remember. If it is not identical in design specification, material, and function, it is a change, and it must trigger the MoC process.
Exactly. Which brings us to step 2. Prepare the organization for change.
This feels like the phase where all the different disciplines of safety you study for the CSP sort of collide.
Step 2 is the heavy lifting. This is where you conduct the risk analysis before a single physical action is taken. You are asking, what new hazards are we introducing to this facility?
So if you're bringing in a new chemical, this is where you secure and review the new safety data sheet. You update the facility's hazard communication program.
You evaluate the need for new personal protective equipment.
What about industrial hygiene? Let's say we are modifying a process that involves cutting masonry, which generates silica dust.
If you are altering a process that changes the generation rate of particulates, you have to bring in your industrial hygiene principles. You have to calculate the new generation rates.
You have to look at your existing local exhaust ventilation, your hoods, your duct velocities, your fan capacities.
And mathematically determine if the current system can handle the increased load. If it can't, the MoC preparation phase dictates that you must upgrade the ventilation system before you implement the process change.
You are also updating the engineering drawings, the piping and instrumentation diagrams, the P&IDs, and rewriting the standard operating procedures.
Which perfectly sets up step 3, implement the change if safe.
I noticed that caveat in Yates's text, if safe. This isn't just a rubber stamp. The safety professional or the MoC review committee holds a tremendous amount of authority here.
That caveat is the ultimate go or no-go threshold. An initiated MoC is a proposal, not a mandate.
If, during the preparation phase, the multidisciplinary team determines that the risks cannot be adequately controlled,
Perhaps the necessary ventilation upgrade is too expensive, or the chemical substitution is too reactive, the safety professional has the authority to halt the implementation. The change is rejected.
but let's assume it is approved and the physical implementation occurs. We then move into the after phases. Step 4 is embedding the changes within the company culture and practices. How is this different from just handing an operator an updated manual?
Handing out a manual is an administrative check-the-box exercise. Embedding the change means ensuring that the operators, maintenance staff, and supervisors truly understand the why behind the change.
It involves verified, documented training, which ties directly into Domain 8 of the blueprint, training and education.
You must assess the competency of the workers regarding the new procedure. Do they understand the new hazards? Do they know how to operate the new emergency shutoffs?
And finally, step 5, execute and monitor the change. You don't just turn on the new machine and walk away, assuming your preparation was flawless.
Yates ties this concept back to Chapter 31's discussion of the Deming PDCA model. Plan, do, check, act.
Continuous improvement is paramount here. The monitoring phase is the check and act portion of Deming's model.
You are monitoring the system to ensure that the change functions as intended and, critically, that it didn't inadvertently introduce unforeseen hazards that your team missed during the risk analysis in Step 2.
Let's put this entire 5-step process into a deep dive scenario. The kind of complex, multi-layered question you might face on the exam.
Okay, let's hear it.
Let's say a manufacturing facility decides to swap out a heavy-duty industrial cleaning solvent used to degrease metal parts. They want to replace it with a new, quote-unquote, greener, environmentally friendly alternative.
On the surface, the environmental management team will be thrilled. The new solvent likely has lower volatile organic compounds, or VOCs, which helps with their air permitting.
And the operations team likes it because it's slightly cheaper. So they bypass the MoC process. They just order the new green solvent, put it in the parts washers, and start using it.
But what happens when we look deeper at the chemistry and the equipment? Because they skipped Step 1 and didn't trigger NOC, they skipped the chemical compatibility analysis in Step 2.
What did they miss?
What they didn't realize is that the chemical composition of the new green solvent, while much less toxic to humans and the environment, is highly corrosive to the specific type of nitrile rubber seals used on the high-pressure fluid valves throughout the facility.
So we have an incompatible chemical interacting with our pressure band.
Exactly. The new solvent slowly degrades those nitrile seals over a period of 2 to 3 weeks. It's an invisible failure.
Until it isn't.
Right. Eventually, a degraded seal completely fails during a high-pressure transfer. You now have a catastrophic blowout of pressurized, heated process fluid.
Let's analyze the fallout of that bypass MoC for the exam candidate. You now have an acute occupational exposure for any worker in the vicinity. That tests your toxicology and emergency response knowledge.
You have a potential fire hazard if the fluid is flammable, testing your fire protection knowledge.
And you have an environmental spill that needs to be contained and reported, testing your EPA compliance knowledge.
All of those cascading failures happen because a seemingly harmless greener chemical bypassed the MoC process. That scenario is the embodiment of the CSP exam. It proves how every technical domain is interconnected. You cannot study these topics in isolated silos.
Speaking of interconnected concepts, let's look at the notes you brought regarding Section 4, the intersection of MoC and prevention through design, or PTD.
Yes, Chapter 35 of the Yates text covers PTD. It defines it as the practice of addressing safety and health needs in the design and redesign process to prevent or minimize hazards.
Usually when I hear prevention through design, I think of an architectural firm designing a brand new greenfield factory from scratch.
That is the traditional view, but it's an incomplete one for a safety professional. Every single time a MoC is triggered in an existing facility, it is a forced opportunity to apply PTD principles.
Because a MoC is, by its very definition, a redesign of a localized process, system, or workstation.
Therefore, the tools, philosophies, and hierarchies of PTD must be rigorously applied during the preparation phase of the MoC.
That makes perfect sense. To understand how to apply it, we need to review the ANSI Z590.3 standard, which is the hierarchy of controls specifically applied to PTD.
Yates outlines this hierarchy from most effective to least effective. Avoidance, elimination, substitution, engineering controls, warnings, administrative controls, and finally, personal protective equipment.
How does a review team actually use this during an MoC?
The primary goal of an effective MoC process should always be to push the risk mitigation strategy as far up that hierarchy as physically and financially possible.
So when a change is proposed, say introducing a new automated cutting tool, the review team shouldn't just look at the exposed blade, accept the hazard, and say, well, we will just buy the operator's heavier cut-resistant gloves and write a new warning sign.
Because that is relying on PPE and warnings, which are the weakest, most easily bypassed controls. They rely entirely on human behavior.
Precisely. Instead, the MoC process should force the engineering team to ask, can we achieve this operational goal by avoiding the risk entirely?
Can we eliminate the hazardous step by outsourcing the cutting? If not, can we substitute the cutting method with something less hazardous, like a water jet, instead of saw blade?
And if we must use the saw, what engineering controls can we design into the system before it is installed? Can we interlock the machine guards so the blade physically cannot engage unless the worker's hands are clear?
I see how the PTD lifecycle maps perfectly onto the MoC lifecycle. The PTD stages listed in the text are pre-design, conceptual, design, build, install, operational, and decommission.
When you are in the identify and prepare phases of an OC, you are functionally operating in the pre-design, conceptual, and design stages of PTD. You are evaluating the blueprints of the proposed change.
But how do you evaluate those blueprints systematically? You can't just stare at a schematic and hope you spot the hazard.
To evaluate those blueprints effectively, the safety professional utilizes specific analytical risk assessment tools. Chapter 35 outlines several of these, and they are heavily tested on the exam under Domain 3, Risk Management.
During the prepare phase of a complex MoC, you have to choose the right tool for the job. You might start with a preliminary hazard analysis, or PHA, to get a high-level view of the major risk categories.
Or, for a simpler procedural change, a structured what-if analysis might be sufficient.
But what about the highly complex advanced tools? The Yates text explicitly details HAZOP and FAEA on pages 791 through 793.
I know candidates struggle with the difference between these two. Let's do a deep dive here. Walk me through how we would actually conduct a HAZOP during an OP.
HAZOP stands for Hazard and Operability Study. It is incredibly common in process safety, petrochemicals, and complex manufacturing. It is a highly structured, systematic team approach.
What's the core mechanic of it?
The core of a HAZ is the use of specific guide words applied to process parameters. The guide words are terms like more, less, none, reverse, part of, or as well as.
And the parameters?
The parameters are physical conditions like flow, temperature, pressure, or composition.
Okay, let's apply that to a hypothetical MOBR. Let's say a facility is submitting a MOBR to install a new higher capacity pump on a pipeline, transferring a hazardous liquid to a reactor vessel.
Yeah.
How does the HAZOP team analyze that proposal?
The team sits down with the proposed piping and instrumentation diagrams. The facilitator takes a specific section or node of that pipeline. They take the parameter flow, and they apply the guide word more.
The question to the team becomes, what happens to our system if this new pump delivers more flow than intended?
And the team would brainstorm the consequences. More flow might overfill the reactor vessel, causing a spill. Or it might increase the reaction rate dangerously, causing a thermal runaway.
Right. Then they take the guide word, none. What happens if there is NO flow?
Perhaps the pump fails, or a valve is accidentally left closed. The consequence might be that the reactor vessel overheats because the incoming liquid was acting as a coolant.
Then they use reverse. What happens if there is reverse flow? Could the hazardous liquid from the reactor flow backward through the new pump and contaminate the supply tank?
By systematically combining every guide word with every parameter, you uncover hidden, highly specific risks in the proposed design.
Once those risks are identified, the team dictates the necessary engineering controls like high-level alarms, pressure relief valves, or check valves that must be added to the MoC proposal before it can be approved.
That is an incredibly powerful tool. It forces you to think outside of the happy path where everything works perfectly. Now, how does that differ from FMEA, failure modes and effects analysis?
While a HAZOP looks at the deviations in the process parameters, an FMEA is a bottom-up reliability tool focused on the specific hardware. It looks at every single mechanical or electrical component being introduced in those again and asks, how can this specific part physically fail?
So sticking with our pump example, an FMEA wouldn't look at the flow rate of the whole system. It would look at the pump itself.
Yes. The FMEA team would look at the pump's motor, its bearings, its seals, its power supply. They would ask, what is the failure mode of the motor?
It could short circuit, it could overheat, the shaft could seize.
For each of those failure modes, they ask, What is the effect on the system? How severe is that effect? How frequently might it happen? And how easily can we detect it before it causes a disaster?
By using HAZOP or FMEA during the MoC's preparation phase, you are actively practicing prevention through design. You are identifying the exact failure points on paper, mathematically calculating their risk, and engineering them out of existence before a single piece of metal is cut.
I love that. You are solving the problem in the abstract before it manifests in reality.
No.
But this brings me to a critical operational question.
Okay.
Let's say we've done the perfect HAZOP, we've applied the hierarchy of controls, we've implemented the change safely, and the new equipment is running. How do we actually prove that our MoC program is effective across the entire company?
That brings us to Section 5, measuring, auditing, and documenting the change.
Because this is a scenario you will absolutely face, not just on the exam, but when an OSHA inspector or a third-party auditor walks into your facility.
Having a beautifully written MoC policy in a binder on the EHS director's shelf is not evidence of a functioning system. A policy is just paper. You have to evaluate the actual execution of the program using concrete performance metrics.
And this introduces the critical difference between lagging indicators and leading indicators, which Yates defines on page 812, and which forms a massive part of Domain 2 on the blueprint.
I understand the biotic analogy. Lagging indicators are looking in the rearview mirror, and leading indicators are looking through the windshield. But how does that actually look when evaluating a MoC program?
Let's start with the rearview mirror. A lagging indicator measures outcomes after the fact, after the failure or the harm has occurred.
Applied to management of change, a classic lagging indicator would be your incident investigation data.
If you're conducting root cause analyses on injuries, spills, or equipment damage, and you repeatedly find that an unauthorized, undocumented modification was the root cause, your lagging indicators are screaming that your MoC program is failing.
If a maintenance tech lost a finger because a machine guard was modified without a MoC review, that is a lagging metric of system failure.
By the time a lagging indicator tells you something is wrong, someone is already hurt, or the plant is already damaged. We need to be proactive. If I'm building a dashboard for the plant manager to show that our MoC program is healthy, what specific leading indicators am I tracking?
Leading indicators measure the proactive, preventative actions taken before any harm occurs. They prove the system is active and engaged. A highly effective leading indicator for MoC would be tracking the percentage of MoCs that successfully completed their pre-startup safety review, or PSSR, on time before the new equipment was energized.
So if 100% of our new installations had a verified safety walkthrough before they were turned on, that's a strong leading indicator.
Exactly. Another one would be tracking the number of hazard communication training hours delivered proactively as a direct result of an MSC. Or you could track the number of MoMIS proposals that were actually rejected or sent back for revision by the safety committee.
Wait, tracking rejected proposals is a positive leading indicator.
Absolutely. If your committee approves 100% of the MoC submitted without a single revision, your committee is just rubber stamping paper. They aren't doing rigorous risk analysis.
A healthy MoMIS program will have a percentage of proposals that are challenged, revised to add better engineering controls, and improved before final approval. Tracking that revision rate proves the system is critically evaluating risk.
That makes perfect sense. So when an auditor comes in, they will look at that dashboard. But auditing is a multifaceted process. Chapter 37 covers safety program auditing techniques. It breaks an audit down into 3 main avenues of investigation: document review, employee interviews, and site condition observations.
Documentation is the bedrock. The blueprint explicitly tests your knowledge of this in Domain 2, Topic 10. Utilize document retention or management principles.
When we talk about modern MoC documentation, we aren't usually talking about a filing cabinet anymore. Large facilities utilize enterprise EHS software. You might see systems like Spiramid, Medgate, Process MAP, or dedicated SAP modules used to track the MoC lifecycle.
How does an auditor approach that software?
The auditor will pull a random sample of completed MoCs from the system. They are verifying the paper trail. And MoC is legally and operationally useless if it isn't documented, retained, and easily accessible.
The auditor will look for the original technical proposal, the documented risk analysis like the 8AZAPI notes we discussed, the signatures of the approval authorities, and crucially, the verified completion of all action items.
If the MoC required a new SDS to be added to the database, the auditor will check the database to ensure it was actually uploaded.
But paperwork only tells half the story. You can have a pristine software database filled with perfectly filled out forms, but a terrible safety culture.
That's why the employee interviews, in the audit methodology are so revealing. You have to leave the office, go out to the manufacturing floor, and talk to the actual operators.
The interviews are where you discover if the MoC program exists in reality, or just in the EHS manager's computer. An auditor will walk up to an operator running a complex machine and ask a simple scenario question.
They might ask, if you notice this machine is frequently jamming, and you figure out a way to modify the feed chute to make it run smoother, what is the process you follow to make that change?
And if the operator says, oh, I just submit a work order, tell Dave in maintenance my idea, and he comes out and welds a new piece of metal on it over the weekend.
Then your MoC program is a ghost. It doesn't exist in the culture of the workforce. The workers do not understand that a modification to a feed chute is a change that requires risk analysis. The audit must capture that disconnect.
Furthermore, the audit checklist must evaluate the cultural authority regarding safety. A critical question to ask operators and mid-level supervisors is, do you have the actual supported authority to shut down a process or halt an installation if you realize an OE procedure was bypassed?
That is the ultimate test of a safety culture. If an operator spots a new, unauthorized chemical on the floor or sees maintenance installing a non-identical pump without a MoC, do they feel empowered to stop the work?
Or do they fear retaliation from management for slowing down production?
If management routinely overrides safety concerns to rush a change into production, the audit must document that catastrophic cultural failure, because that is the exact environment that breeds normalization of deviance.
Okay, we have covered an immense amount of technical and operational ground. Let's synthesize this entire deep dive and bring the focus back entirely to your exam preparation strategy.
Back in Chapter 1 of the text, Yates gives straightforward advice on knowing your strengths and weaknesses and developing an examination preparation plan. How should a candidate take everything we just discussed and apply it to their study routine?
The single most important piece of strategic advice we can offer is to stop studying these safety domains in isolated silos. The BCSP does not test that way, and the real world does not operate that way.
Candidates often study toxicology on Monday, ventilation on Tuesday, and management of change on Wednesday, treating them as separate subjects.
But as we've demonstrated today, a single complex exam scenario will weave them all together.
Exactly. You might see a question detailing a worker who is experiencing symptoms of chemical overexposure. The question will require you to use your toxicology knowledge to identify the exposure limits.
It will require you to use your ventilation knowledge to calculate the necessary capture velocity of the exhaust hood.
And it will require you to use your management of change knowledge to dictate the procedural steps required to approve the installation of a larger fan motor to achieve that velocity.
Here's where it gets really interesting. Understanding management of change is quite literally the skeleton key to the entire exam.
If you deeply fundamentally understand how a facility manages change safely, you inherently must understand the risk assessment methods like HAZOP and FMEA used to evaluate that change.
You inherently understand the ANSI Z590.3 hierarchy of controls and prevention through design principles used to mitigate the risk. You understand the auditing techniques, the leading indicators, and the continuous improvement cycles required to monitor the change.
MoC touches every single domain on the blueprint.
To solidify this interconnected web in your mind, I highly encourage you to use a mental visualization exercise during your studies. Think of a brand new, highly complex, automated piece of machinery arriving on a flatbed truck at the loading dock of your hypothetical facility.
And then mentally walk that piece of equipment through every step we've discussed today.
Yes. First, identify it. It triggers the MoC process because it is not a replacement in kind. It's a new introduction.
Mentally walk it through the PTD evaluation. Ask yourself, how are we engineering out the pinch points and nip hazards before we bolt it to the floor?
Visualize the safety team conducting a what-if analysis. Mentally update the hazard communication documents for the new lubricants it requires. Visualize conducting the competency assessments for the operators.
And finally, mentally conduct the audit 6 months later, checking the leading indicators to ensure the change was embedded successfully and no safety protocols have degraded.
If you can visualize that entire interconnected life cycle, you are more than ready for any scenario the exam throws at you.
That is a fantastic...
Let's briefly recap the massive journey we've taken on this special QHSE Talks deep dive. We started by decoding the undeniable high-yield value of management of change on both the ASP and CSP blueprints. proving it accounts for a huge portion of your grade across multiple domains.
We unpacked the foundational anatomy of MoC, exploring how ISO 45001, OSHA process safety management, and EPA risk management programs demand rigorous change control to prevent catastrophic occupational and environmental disasters.
We walked step by step through the definitive 5-phase process, prior, during, and after, highlighting the critical dangers of failing to identify a replacement in kind.
We then bridge the gap between MoC and the proactive, risk-eliminating power of prevention through design, utilizing complex analytical tools like HIO and FMEA to engineer out hazards during the preparation phase.
And finally, we locked the entire process down with rigorous auditing techniques, emphasizing the necessity of measuring success through proactive leading indicators, EHS software documentation, and brutally honest employee interviews.
To you, the candidate dedicating your time to listening to this, mastering this web of interconnected concepts will absolutely help you conquer the BCSP exams.
But far more importantly, deeply understanding how to manage risk during periods of transition will make you an elite, highly effective safety professional in the real world. You will be the person capable of seeing the invisible hazards and preventing the disasters before the first alarm ever sounds.
Before we sign off, I want to leave you with a forward-looking thought, a concept to mull over as you continue your studies. The CSP exam blueprint is constantly evolving to match the reality of modern industry. Domain 8 explicitly mentions artificial intelligence as an emerging training and educational method.
But AI is also rapidly entering industrial operations, automated manufacturing, and process control.
That is a fascinating frontier, and it raises a profound question for the future of our profession. If management of change is fundamentally designed to control risks when systems evolve, how will you, as a future certified safety professional, apply MoC to the rapid integration of artificial intelligence in the workplace?
How do you effectively manage, audit, and document a change when the machine or the algorithm controlling the hazardous process is constantly learning, shifting, and changing its own parameters dynamically in milliseconds without waiting for human intervention or a signed approval form?
How do you perform a HAZOP on a system that is redesigning itself? That is a heavy, thought-provoking question, and it is undoubtedly the next massive challenge for the safety profession to solve.
Thank you all for joining us on this exhaustive, special QHSE Talks deep dive into Chapter 38. We wish you the absolute best of luck on your certification journey, whether you're tackling the ASP or the CSP. Keep studying, stay relentlessly curious, and always remember that the pursuit of safety is a continuous cycle of improvement.